So I think this week's problems maybe were a little bit harder. I think there were a couple that I don't think anyone got. So I'll go through all of them, and then some of them some people got. So we can go through them together. So the first question, the first combinatorics question on the test was this one. It was, there are 8 red marbles and 8 yellow marbles in a bag. One person, Anna, reaches into the bag, randomly takes out 2 of the marbles. Then second person, Carly, reaches into the bag and randomly takes out 2 of the remaining marbles. And then the question is, what is the probability that they pick the same color combination of marbles? So I guess one way to start with this problem is, let's think about what are the possible color combinations that Anna and Carly could have picked, and what does it mean for them to have picked the same color combination? So does anyone want to volunteer what color combinations are possible?
Could have red and red, could have yellow and yellow, and we could have red and yellow.
Yeah, so it could be red, red, or it could be yellow, yellow, or it could be red and yellow. So since we have these different cases, we might think to solve this using casework. So we could first compute the probability that Anna and Carly both pick red marbles, compute the probability that they both pick yellow marbles, and then compute the probability that they each pick 1 yellow and 1 red marble. So if we write out this probability, I'll just call them Anna and Carly, pick A and C for Anna and Carly, the same color combination. If they satisfy any of these cases, like if they pick 2 red or 2 yellow or 1 red, 1 yellow, all of them would result in picking the same color combination. So we can sum the probabilities in this case. So if we take the probability that they pick 2 reds plus the probability that they pick 2 yellows plus the probability that they each pick 1 of each, that equals the probability that they pick the same color combination overall. So this is probability A and C both pick 2 reds plus Does that make sense to everyone so far? All right.
Yes.
So if there are no questions, then let's calculate the probabilities. So what's the probability that Anna picks 2 red marbles? So how many ways can Anna pick 2 red marbles out of the bag?
8, choose 2 ways.
Okay. And then how many total ways are there for Anna to pick 2 marbles out of the bag?
16, choose 2.
And then what about Carly? So if Anna picks 2 red marbles, then Carly also needs to pick 2 red marbles. How many ways are there for Carly to pick 2 marbles that are both red after Anna has already taken 2 red marbles out of the bag?
6, choose 2.
That'll be 6 choose 2 over 14 choose 2.
Right, yeah, both of you are right. So 14 choose 2. Cool. So this is actually simplifies to 8 times 7 times 6 times 5 over, well, I'll write it out. So 8 times 7 over 2 times 1 times 6 times 5 over 2 times 1 over 15 times 15. Right? And then we can kind of cancel all these denominators. 6 times 5 over 16. And we can simplify this, but I'll simplify it later. All right, so we've done one. What's the probability that they both pick 2 yellow marbles?
The same probability.
Yeah,
reds.
so there's the same number of yellows as there are reds, so it's actually the same. So this is the same as the above. All right, and then the last case is we have probability that they each pick, so both of them pick 1 red and 1 yellow. So how many ways are there for Anna to pick 1 red and 1 yellow?
Would it be 8 choose 1, 8 choose 2, 8 choose 1, and then 8 choose 1 again over 16 choose 2?
Sorry, say that again. So 8
choose 1 times 8
Okay,
choose
8 choose
1
1.
over 16 choose 2.
Okay. And then what about for Carly to choose 1 yellow and 1 red after Anna has already chosen 1 yellow and 1 red?
7 choose 1 times 7 choose 1 over 14 choose 2.
Yeah, awesome. So then this gives us 8 times 8 times 7 times 7 over 2 or 16 times. Which is 2 times 2 times 8 times. Cool. Any questions about this so far? If not, then we just have to sum them and simplify. So if we go back, the original quantity we wanted, this one, we can calculate that by summing all these parts that we've computed already. So the probability that they pick the same color combination equals this first one. Well, since the case for the reds and the yellows are the same, I can just do 2 times 8 times 7 times 6 times 5 plus what we have here on the right. And now, instead of multiplying it all out, we can cancel some of these factors to simplify it more before we have to multiply. So, for example, we can cancel out the 16 in the denominator with the 2 and the 8 here. We could also cancel out the 14 here, as well as here. So now this gives us on the top 3 times 5 over 15 times 13 plus 8 times 7 over 15 times 13. So this gives us 15 plus 56 over 15 times 13, which gives us 71 over 195. Any questions on this problem? Oops, let me try to zoom out here. Any questions? All right, let's move on to the second question then. So this question says, Albert draws 4 cards without replacement from an ordinary deck of 52 playing cards. Find the probability that he draws at least one face card, Jack, Queen, or King. So does anyone have any ideas on how we could do this based on the techniques we learned this week?
Well, we can do it by using complementary probability and finding out the probability that he draws no face cards.
Well, yeah, totally. So this is one where complementary probability will help, because if we think about it, if we directly count how many ways you can draw at least one face card, that's going to be a lot of casework. But the complement of that is pretty straightforward to count. So I'll just write what you set out. So probability Albert draws at least one face card equals 1 minus the probability Albert draws no face cards. So what's the probability that Albert draws no face cards? So we want to count how many ways are there for Albert to draw no face cards over how many total ways there are for Albert to draw 4 cards. So let's start with maybe the denominator. How many ways are there for Albert to draw 4 cards?
52, choose 4 ways.
Yeah. And then how many ways are there for Albert to draw 4 cards when none of them are face cards?
Well, what I did for this one was that I subtracted the total number of face cards from the total number of regular cards, which was 52. There's 12 face cards, so I ended up with 40 leftover cards. And then I sort of drew the different places of each of the cards and then just subtracted by 1 and multiplied 40 times 39 times 38 times 37.
Yeah, that's close. So definitely we want to do the first step of like how many face cards there are. So there's 4 suits. Remember, there's hearts, spades, diamonds, and clubs. And then for each of those, there's 3 different face cards, Jack, Queen, King. So 4 times 3, there's 12 total face cards. So that means there's 52 minus 12, or 40 non-face cards in the deck. So the number of ways that Albert can draw 4 of them is actually going to be 40 choose 4. So you will have sort of the 40 times 39 times 38 times 37 in the numerator, but you have to take into account the ordering. If in the denominator you're also taking into account the ordering. So then here, if we simplify, we're going to get 1 minus 40 times 39 times 38 times 37 over 52, 51, 50, 49. So you can see that if we decide to do 52 choose 4 and 40 choose 4, we're basically counting the number of ways Albert can draw 4 cards, regardless of the order in which he draws them. And that's going to be the same ratio as if we count in both the numerator and the denominator, the number of ways Albert can draw 4 cards, and the order matters. So you could have solved this either way. And then to calculate this fraction, again, we will want to cancel out some factors. So let's see what we can do here. 40 and 50 can kind of cancel. Get 4 and 5. We can cancel like the 3 and 39. And this divides this 17 times. We can 4 goes into 52 13 times. And I believe that's right.
13 can
Am I
cancel
missing any
13.
factors? Sorry?
13
Oh
cancels
yeah,
13.
thanks. I was like, I think we can cancel this more. Okay, cool. I think that's what we have now. And then if we multiply this out, I believe we'll get something like 1 minus, I think the top becomes 1406. The bottom becomes 4165. You can check my math here. And then if we do 1 minus that, that is actually 4165 minus 1406 over 4165, which is 2759. And so that's our final answer. Any questions on this one?
No, please.
Cool. So just to like recap techniques. So this first question, we used casework. This question, we just use complementary probability. All right, let's do this one. So now we have another probability problem. This one says, what is the probability that a random 4-digit positive integer has at least one digit that is a 6, 7, or 8? Any ideas on how we could do this one?
So I did complementary probability for this one, and I was looking at numbers, 4-digit positive numbers without 6, 7, or 8.
Cool. So yeah, again, here we could do complementary probability. So probability, a random 4-digit integer has at least 1, 6, 7, 8 digit equals 1 minus, that's a bad one, 1 minus probability, the random has no 6, 7, or 8. So how do we compute the probability that a random 4-digit integer has no 6, 7, or 8?
First, we'd have to find the total number of 4-digit positive integers. So that's from 1,000 to 9,999. And when you subtract 999 from all of these integers, you end up with 1 to 9,000. So there's 9,000 for the denominator.
Cool. Yeah, that's right. There's a couple ways we could count this. So as an aside, so basically we need to count how many 4-digit integers are there. So one way, as you mentioned, we want to count how many numbers are there from 1,000 to 9,999. And we can count this by basically doing 9,999 minus 1,000 plus 1, which gives us 9,000. Another way we could count this is by saying, okay, well, for our 4-digit positive integers, we can basically count the number of combinations of digits we can put together. So if we think about it as having 4 digits, there's 9 choices of digits that go in the first spot, because it could be 1 through 9. And then for each of those, there's 10 choices for any of these digits. So if we multiply these together, then we get 9,000. So there's just different ways that we could count this. So how do we count the numerator? So we want to count how many 4-digit integers have no 6, 7, or 8.
So I placed all the digits out, and then under each individual one, the number of possibilities. So for the first number, there were 6 possibilities, because we're not using 6, 7, or 8 or 0. And then after that, there was 7 possibilities afterward for each one.
Right, so the 6 possibilities here, there are 1, 2, 3, 4, 5, 9, right? And then for each of these, there's 7 possibilities because you have 1, 2, 3, 4, 5, 9, and 0. So the total you're going to get is 6 times 7 times 7 times 7. Total positive integers, 4-digit integers without 6, 7, or 8. So if we plug that in over here, we get 6 times 7 times 7 times 7. And then the next step would just be to simplify this. So 6 divides 9,000. I believe 1500 be the result. So we have 1 minus 343 over 1500, which gives us 1157 over 1500. Any questions?
No, please.
Awesome. Okay. Here we have something a little bit different. Or I guess before I move on, let me just annotate what we used here. Here we also use complementary probability, right? And before we kind of move on to the other problems, I want to highlight one thing that might be a clue to use complementary probability is like at least one. So when we want to calculate the probability that there's at least one of something, then the complement is that there's none of that thing. And so oftentimes it can be easier to count when there is none of something than when there's at least one. And so in this problem, again, we said there was at least one digit. So it's kind of a clue to potentially consider a complementary probability. It's not going to be 100% of the time, but it's a good clue to look at. All right, so now let's move on to something different. This one says 2 points are randomly and independently chosen on a circle. What's the probability that the distance between the points is less than the radius of the circle? So what I like to do here is let's start with a diagram because it helps us visualize the problem when it's sort of a more like geometry type problem. So I'm going to try to draw, actually, can I draw a circle? Let's see if this works. Oh, cool, I can draw a circle. Okay. So we have a circle. And then we pick 2 points on the circle. I want to say what's the probability that the distance between the points. Let's say you pick a point. Let's say this is the center of the circle. This is the radius, we'll call it R. Then we pick another point. What's the probability that this distance between point A and point B is less than R? So any ideas on how we could do this one? This one, I think a lot of people got this problem right.
Well, I drew a circle from half radius to another half radius, because anything within that circle, any 2 points within that circle will have a distance less than the radius.
Do you mean where's the center of the circle? With center A?
Like so I divided the diameter into 4 parts, and I took this 2 centerpieces, and then because those form, because that gives the circle that I just drew a diameter of the radius, any 2 points within that circle would not be greater or equal to the radius.
Do you mean you want to divide this line into 4 parts? Like this?
No, I divided the diameter into 4 parts.
Okay, so like this.
Yeah.
And then you drew the circle?
Yeah.
Okay. I'm curious, what did you do with the circle?
So I realized that if I were to put any 2 points within that circle, they wouldn't meet because of the fact that the circle has a radius that is equivalent to, has the radius as its diameter. So
I see.
in any case, it will always be less than. So I calculated the area of the circle and then calculated the area of the larger circle and put that as the probability, the area of the smaller circle over the area of the larger circle.
I see. Okay, gotcha. I think that it's calculating a different probability, so maybe I'll explain why it doesn't quite work. So in this case, the problem says we're picking 2 points on a circle. So that means the points that we're picking, they need to be on this like green, like the circumference of the circle. So we're not actually choosing points inside the circle. So in this case, if we draw, we don't necessarily want to look at areas because what we're picking on is sort of a one-dimensional thing. It's like on the circumference. And so where we want to compare areas is when we're saying, hey, what's the probability that we choose something inside the circle? And then depending on what it is that we're choosing, then you can compare areas. So what you said would be a good solution to the problem, like what's the probability that, so say I pick a point randomly in the circle, what's the probability that it's within half the radius of the center? Then you would do that. But what we could do in this case is we want to find the set of points on the circumference of the circle such that 2 of them are less than, the distance is less than the radius apart. And what we could do here is notice that it doesn't really matter what the first point we choose is. We can arbitrarily choose any point on the circle. And then what we really want to calculate is, given that we chose, say, point A on the circle, what's the probability that the second point we choose is within distance r on the circle? So there's a couple ways you could do this. The one way is we can kind of notice that if it's distance r, then basically anything, let's like draw this out. Suppose this is r and this is r. Then anything within this arc is going to give us something where the distance between A and B, let's call the second point B, distance less than or equal to R. Anything in this other part of the circle will give us a distance that's greater than R. So we can compute basically the distance of this arc divided by the total circumference. And one way to compute the distance of this arc is we kind of look at, well, if this is R and this is R, and I'm going to draw this line as well, these are R, then we're forming these equilateral triangles. And we had a very similar problem in class, actually, where because these are equilateral triangles, we know, for example, this is 60 degrees, this is 60 degrees. And so this is actually going to be 120 degrees of the circle. So if we wanted to compute this arc length, we could basically do 120 degrees out of 360 degrees times the circumference. So if we wanted to calculate the probability that second point is within R of first point, we could basically take the purple arc length over total circumference, which is 120 over 360 times the circumference, we'll call it C, over C. So this gives us 120 over 360, which gives us 1/3. So basically you can just compare the angles. So this is 120 over 360, or you could actually compute the arc lengths. You'll see that a lot of things will cancel out because this will be actually like 1/3 pi times 2r. So it's 2/3 pi r. And then the total is going to be 2 pi r. And you'll end up with 1/3 as well. So there's a couple of different ways you could do this.
Wendy, please, you said the arc which is in red will be the radius of that will be larger than the one in purple, but you get 6 equilateral triangles in the circle. So why would that one be greater than the one in the purple?
Yeah, so basically, if you have a circle, all right, so I drew a lot here. Let me just start over. So basically, remember, we have a circle, and we have the radius is r. And the question is basically saying, what's the probability that we pick 2 points and their distance is less than r? And so we could rephrase this question to say we've already picked a point, any point on the circle, and then we randomly pick a second point. What's the probability that that second point is within R? So another way you could see this is for any point to be within a radius of R of A, we could draw the circle of radius R around A, which would look something like this. And it would intersect the circle at 2 points where this is R, because they're radii of the circle around A. And then basically any point from A to within the circle is going to be less than R, and any point from A to outside the circle is going to be greater than R. So that tells us that what we really want to compute is this arc length over the total arc length. It's another way to see why it's from this point to this point on this arc. Does that answer your question?
Yes, thanks.
Yeah. All right. Let's move on to the next question. This is another geometry and probability question. This one says a point P is randomly selected from the interior of square ABCD. What's the probability that the length of segment AP is greater than the length of AB? So a couple of things here. One, again, we want to start with a diagram, but want to make a point here where last time I talked about how the problem said a point was selected on a circle, and so it was selected on sort of a curve, and so that was a one-dimensional thing, so we want to compare lengths. Here it's saying selected from the interior of the square, so we're selecting from an area. So this is a clue that we're probably going to be comparing areas. So let's try to draw this out. I found this cool tool so we can draw a real square. Try to. Okay, so let's call the square ABCD. And it says we randomly pick a point from inside. What's the probability that the length of that point is greater than the length of AB? So we can maybe give a length to AB. Maybe we could call it X or something like that. And since it's a square, all of these points, all of these sides have length X. And then the question is, say I pick a point P, say I pick a point P here. What's the probability that this line AP, the distance is greater than X? So how do we find the set of points such that AP is greater than X? Any ideas?
Well, one thing I noticed when I was solving the problem is that if we look at AB as a line, and since this is a square, we can draw an arc from B to D to signify these are all these lengths would be less than or equal to AB if we were to put point B within that arc.
Yeah, so kind of similar to the previous problem, if we want to find the set of points P such that AP is less than X, then we can draw a circle of radius X around A, which would look something like this. And it'll kind of keep going here. We have a big circle around A with radius R, or sorry, radius X. And that's going to be the set of points that have distance X or less to A. And if we intersect that with the square, then what we have is this little wedge of the circle. And anything within the circle is going to have distance less than X. And here we said, what's the probability that the length of the segment is greater than the length of AB? And so we really want to calculate this area, or we really want to select a point from this area. So any point we select in this shaded area is going to give us a distance greater than X. Does everyone see why that is?
Yes.
Cool. So let's actually calculate this now. So the probability length of AP is greater than of length of AB equals sort of orange area over area of the square. So how do we calculate the orange area?
It would be the area of our arc and subtracted from the area of the square, and that would give us the area in orange.
Okay, so it's the area of the square minus area of, I'll just call it the sector, the circle we have within the square over the area of the square. Cool. So what's the area of the square if the side length is X?
X squared.
Okay. And then what's the area of the sector?
Pi
So
over
we're
4.
talking about this sector, right? Yeah, sorry, say that again.
Pi over 4.
So the area of a circle is pi r squared. And then this is 1/4 of a circle. So it's 1/4 times pi, and in this case, r is x, so x squared. And then we see we can actually cancel out the x squareds. So then we get 1 minus 1/4 pi over 1, which is basically 1 minus pi over 4. So you could write this as 1 minus pi over 4, or you could write it as 4 minus pi over 4. I will accept both answers. Any questions on this one? All right, I'll move on to the last one. So this one was the show your work question. This question says if x is greater than or equal to 0 and less than or equal to 5, and y is less than or greater than or equal to 3 and less than or equal to, greater than or equal to -3 and less than or equal to 3, find the probability that x and y, or x plus y, is greater than or equal to 0 and less than or equal to 3. So I want to just call out, I graded this question. A lot of people computed the probability correctly, assuming that x and y are integers. But in this case, because x and y could be any numbers between 0 to 5 and between -3 to 3, we actually want to count the probability again by areas. And kind of graphing it out rather than assuming that x and y have to be integers. So if the problem had said, x and y are integers, then we would count the probability potentially by kind of just counting like different cases. We could do it that way. But since it doesn't say that x and y have to be integers, we have to account for the case that x and y could be, like 0.3 or 0.5 or anything like that. So let's start by graphing this out, and then we can see how we count the probability. So let me try to draw, let's see if I can draw a line. Cool. So all right, so let's just graph this on a normal coordinate plane, x and y. And it says x is between 0 and 5, and y is between -3 and 3. So I'll just kind of draw some as best as I can. I'll space it out. So first, let me draw out maybe x and y. So y is between -3 here. So this is the line y. So y is greater than or equal to -3. And here is y is less than or equal to 3. So that's like the shaded area down here, and this is the shaded area above there. For x is between 0 and 5, a slightly different color. So x is greater than 0 is just this line. This is the line, x is 0. So if x is greater than 0, it's everything on this side of the line. And if x is less than or equal to 5, it's this line right here. And it's everything on this side of the line. So if we put that together, then what we have is we basically have the constraint that x and y are in this rectangle. With the corners at, so this is -3, 0. This is -3, 5. This is 5, 3, and this is 3, 0. Any questions so far? Did I graph that correctly?
I think your coordinates are a bit off.
Oh, sorry. This one should be, you're right. I confused X and Y for some of these. 5, -3, 0, -3, 0, 3. Did I fix that right? Thanks for checking my work. All right, so let me shade in this area now. So this area represents 0 is less than or equal to x less than or equal to 5, and -3 is less than or equal to y less than or equal to 3. All right, so now let's look at x plus y is greater than or equal to 0, and x plus y is less than or equal to 3. So take a different color to graph this, maybe blue. So if we want to graph x plus y is greater than or equal to 0, then that's going to look something like this. It's going to go through the origin, and then it's going to go kind of down with slope -1. So I think it's going to intersect this at 3, -3. So this is the line x plus y greater than or equal to 0, and it's everything on this side of the line. And then similarly, x plus y is less than or equal to 3. We're going to start with the this intercept at 0, 3, and then it also has slope -1. So it's kind of going to intersect here. And then again at this point, it's going to be 5, -2. So if I draw this line, this is the line x plus y is less than or equal to 3, and it's going to be everything in this area. So now if we combine this with what we have, which is that x is within the square, then we see that when, I'll just shade this in, 0 is less than or equal to x plus y is less than or equal to 3, is basically everything in between these blue lines. And in particular, we care about the area within the square, which is this area right here. So if we pick any x and y within this area, then we're going to satisfy this inequality. Any questions so far?
No, please.
All right, so there's a lot of colors, but let's go back to finding the probability. So I think we have all these things drawn out now. So now we can compute the probability that 0 is less than or equal to x plus y is less than or equal to 3 if 0 is less than or equal to x less than or equal to 5, and so this is just the blue area, which is when all these constraints are true, over the yellow area, which is sort of our condition of x is between 0 and 5 and y is between -3 and 3. So how do we calculate, let's start with the yellow area. How do we calculate the yellow area?
Well, that would be 5 times 6.
Yeah, so we have that this length is 5. This length is 6. So it's 5 times 6. And how do we calculate the blue area?
The area of the triangles formed by the lines. So the area of the smaller triangle is 3.
Are you talking about
And
this
then
triangle
the
right
area
here?
of,
Is this a triangle you're talking
yeah,
about?
both, yeah. And
Okay.
then the area of the other triangle
So we want to
is
basically subtract
15.
out the area of these two triangles, right? Is that what you're saying?
Yeah.
Cool. So this triangle has side length 3 on both sides. This one has side length 5 on both sides. So the area of the triangle is 1/2 times base times height. And then the area of the larger triangle is also 1/2 times base times height. Base and height are 5. So this becomes 30 minus 9 over 2 minus 25 over 2 over 30, which is 30 minus 34 over 2 over 30, which is 30 minus 17 over 30, which is, I'm just writing, which is 13 over 30. So that's going to be our final answer. Try to zoom out a little. Any questions on this one? All right, so that was all the questions on the combinatoric side of the test. If there are no more questions on that, then I'll let Matthew talk about the geometry ones.
Okay, let's start with the first problem. And let's draw ourselves a figure. And you know what? I drew that a little bit too isosceles. It's good to get practice drawing diagrams and figure out the things that we need to do in order not to fool ourselves. Okay, so parallel lines give us equal angles. Equal angles give us similar triangles. And similar triangles give us ratios. I'm going to go ahead and write them all out, even though we're not going to use them all. And now let's look and see where we have good solid information. Okay, we have a ratio of similitude of 1/3. And we are interested in PY. That's the thing that we know right there. And we have PY over PR, but we don't know PR. But you know what? We can rewrite PR as PY plus 8. And now we have an equation we can work with, and I will cross multiply. 5 times PY plus 5 times 8 equals 15 times PY. Subtract 5 PY from both sides. And we get the PY equals 4. Any questions or thoughts about this one? And I think I saw the answer 8/3 on a few papers. Don't get too quick with your use of the similarity ratio. Remember to be deliberate in your setup. Some of you got that 1-to-3 ratio, and then you made PY to YR a 1-to-3 ratio. But it's good to be deliberate in the setup, and that's one of the good things about writing everything out, is that we can see, oh, hey, this is not YR right here. YR plus PY equals PR. Any questions or thoughts about this one? Okay, moving to number 3.
No, please.
Sorry? Was there a question?
I just said no.
Okay. So this one is not the hardest question on the test, but you know what? I actually didn't cover this while we were working. So those of you who got this did a great job. But I'm gonna talk about an idea before we go any further. I'll go ahead and teach it now. It's definitely solvable without having the conversation, but let's say that we have 2 similar figures, and I'll just use the example of 2 similar triangles. Actually, first, even before 2 similar triangles, I'm going to make a doodle. If we put evenly spaced out points, the same number of evenly spaced out points on a triangle, and then connect points parallel with each one of the sides, we get a bunch of little triangles. And I'm sure that some of you have made this doodle on your own before. Well, let's count these triangles. If we count by row, we can see that we have consecutive odd numbers on the rows, and those consecutive odd numbers wind up being a perfect square if we add them up. Okay, so the ratio of the big triangle, the area of the big triangle, to the area of one of the little triangles is 3 squared. Is that always going to be true, that we're going to have a square of the number of edges along the side length of the big triangle? Anybody?
Mr. Crawford, could you just repeat that again up to from the 3 squared part?
Sure. I want to know, do we always get a ratio of area that is a square? The square of the number of edges, 1, 2, 3, of one of the small triangles that make up the edge length of the big triangle.
Yes, I think we do.
We do. If we use our Gaussian method for summing the terms in an arithmetic series, we get n terms that are each 2n right here, and we quickly find out that yes, s is n times n squared. So does this happen more generally? Let's say that we have these two triangles, and let's say that we have side lengths of A, B, and C over here, and then AR, BR, and CR over here, where R is the ratio of similarity, the ratio of similitude, and we want to know what is the ratio of the areas. Well, I'm going to drop an altitude to the corresponding base of each of these triangles. And now look, we said these triangles are similar. Well, that means that that angle and that angle are the same. So what is it that we notice?
AA similarity.
AA similarity. Good work. Yeah, triangle, right triangle, A, B, D is similar to right triangle, X, Y, W by AA similarity. Okay, well, what does that mean? It means that the ratios of the sides, like for instance, I'm going to go X, Y, W on top. X, Y over AB is the same as YW over BD. And the first one right here, we know this. This is CR over C. So the ratio is just R. Okay, so if we were to call the altitude, if we were to let H equal the altitude to side AC in the smaller triangle, then we need H times R to be the altitude YW of the larger triangle. So now let's see, what is the ratio of the areas of these two triangles? Using our simplest formula for the area of a triangle, 1/2 base times height, and 1/2, 1/2 BH in the bottom, and then 1/2, well, the base of the bigger triangle is B times R, and the height is H times R. And when we cancel everything out, we just get R squared. So I'll go ahead and take this a step further. If we have similar figures in 2 dimensions, the ratio of their areas is the square of the similarity ratio. If we have similar figures in 3 dimensions, proportionally the same, then we are stretching the measure of the volume 3 times R each time. So we have a ratio of R cubed among similar 3-dimensional figures. So now what does that mean here? What is the similarity ratio between these 2 triangles?
Three.
3. Okay. So let's see how that helps us. For the smaller one, let's see, AB equals 9 and BC equals 12. We want the altitude XZ, so we want the altitude to BC. Okay. I'm going to draw BC in the smaller triangle, and that's 12, and then AB equals 9. I'm not sure exactly what angle that is, but I'll just kind of draw it like that. Okay. And I did this because in the bigger triangle, let's see, X is to C. X is right here corresponding with C. Z is corresponding with B. And Y corresponds with A. And we want the altitude to XZ, which corresponds to the altitude to BC in the smaller triangle. Well, we have a base with the smaller triangle. We're going to work in the smaller triangle and just multiply our answer by 3 because we know that similarity ratio. With the smaller triangle, the easiest way to get the altitude is to make use of the given area. So base times height divided by 2 equals 40. Now we multiply that by 3 and we get 20 as our answer. Any questions or thoughts about this one? Okay, let's move on to, well, number 5. We'll go ahead and work number 5, and this is my fault. I copied the wrong problem here. So we had a proof-based problem in the middle of the short answer portion. Let's go ahead and figure out what we would do in this problem. Okay, those sides are all equal to each other. Now here's what we know. Because we have isosceles triangles, angle MBA equals angle MAB. We also know that angle MAC is equal to the measure of angle MCA. And we know that the sum of all of the angles of a triangle is 180. And by the way, I know that when I was young, I definitely would have just thrown down variables and said, oh, 2x plus 2y equals 180 degrees. I try to connect myself to thinking more directly in terms of the geometry by writing out the angles in the traditional way. But I absolutely just, if I'm doing my work on my own paper before I write a proof, I absolutely just throw down common variables and do all the algebra that way. And so angle A, well, that's angle MAB plus angle MAC. And then we have angle B is angle MBA, and then angle C is angle MCA. and angle MAB is angle MBA. And angle MAC is angle MCA. So we have 2 times that sum right there. I'll just go ahead and divide by 2. Oh, I should have converted the other way. Oops. I substituted in the wrong direction to make this as simple as possible. But since angles MBA and MAB are the same and MCA and MAC are the same, now we have MAB plus MAC, and that's just angle A. So we have a right triangle. Any questions or thoughts about this one? Okay, let's move on to problem number 7. Two similar right triangles have areas of 6 square inches and 150 square inches. The length of the hypotenuse of the smaller triangle is 5. What is the sum of the lengths of the legs of the larger triangle? I'm going to go ahead and let the legs of the smaller triangle be A and B. And for the larger triangle, well, notice the ratio of the areas is 25 to 1. So what is the similarity ratio?
1 to 25.
25 to 1 is the ratio of the areas. So the ratio of the length is 5 to 1. So we have 5A, 5B, and 25. Clearly, I've drawn the triangle too small, but that's okay. We want the sum of the lengths of the legs of the larger triangle. So what we're really looking for is 5 times A plus B. Okay, well, let's see what kind of information we have here. Well, by the Pythagorean theorem, we know that A squared plus B squared equals 5 squared. Also, because of the area of the smaller triangle, we know that A times B divided by 2 is equal to 6. And I'll go ahead and rewrite these equations. The second one, let's see. Well, the first one, A squared plus B squared is 25. And with the second one, A times B is equal to 12. And we're wondering how to work with these equations. Well, here's the thing. We don't actually have to solve for A and B. We could try some substitution, or we could square the second equation and then try substitution, but we don't even need to go that far. If we're trying to relate these equations to A plus B, well, we've got these squared variables in there, A squared and B squared, which means, hey, maybe we should try to relate this to the square of A plus B, which is A squared plus 2AB plus B squared. Okay, we can get that from this system of equations. We can add the first equation to twice the second, and we get A squared plus B squared plus 2AB is 25 plus 2 times 12, which is 49. So If a plus b squared is 49, then a plus b is 7, in which case 5 times 7 equals 35. And I'm going to venture a guess. I saw some people answer 60. And I think what some people did was found the perimeter of the larger triangle and did not subtract out the hypotenuse. And I suspect that some of you just grasped onto the 3, 4, 5, the smaller triangle is a 3, 4, 5, and scaled it up and got a 15, 20, 25 triangle, and then didn't check back with the answer. Whenever it is that you do any substantial amount of work with a problem, it's good to go back and reconnect to the problem. What am I being asked? Sometimes I do this in the middle of a problem. When the problems get harder, especially at the Olympiad level, I probably, well, it depends on the type of problem, but I very often, every time I make substantial progress, go back and reconnect with the problem. What is it that I'm trying to do? Sometimes that's a matter of just simply not putting down the answer to the wrong thing. But with harder Olympiad problems, it's really a matter of like reframing. You simplify the end game sometimes by working backward, or you take information and you move forward with it, and you want to reframe what you're trying to do with that information. Any questions or thoughts about this one? Okay. Let's move on to number 9. I like this problem a lot. We talked about the fact that there is no SSA similarity. And some people just go, okay, so there's no theorem. But in a sense, there is. With similarity or congruence, sorry, I should have said congruence. SSA congruence doesn't exist as a congruence theorem. However, our congruence theorems take infinitely many possible triangles and say, well, there's only one that has this set of information. However, in the case of SSA, it's not like there's still infinitely many possibilities. Instead of going down to one, there are 2 possibilities. And so this is actually quite an information boost. It's not quite congruence, but it's highly restricted possibilities. So what can we do here? We're going to draw a diagram in the same way that we drew diagrams when we established the congruence theorems. What I'm going to do is draw a segment AB of length 13. And then we know that BC has to be of length 10. So C is somewhere on this circle. And then angle A is 40 degrees. Now I could draw down this way. I'm just going to, we know that this is just going to be a mirror image. So I'm just going to draw upward this way. And we find that there are only 2 possible locations of the point C. So now we have this diagram and we want to know the sum of the possible values of B. So that plus that. Well, we know we have a 40-degree angle here. And we look around for more information in the diagram and we realize, oh, well, we've drawn this circle, so that is the same as that. Well, now we have an isosceles triangle. Okay, I'm going to throw down a variable name. I'm just going to call these angles X and X right here. And what that means is that angle C1B C2 is 180 degrees minus 2 times X. And I don't know what X is yet, but maybe we don't need to know. Well, since the interior angle of triangle C1B C2 is X at C1, the exterior angle at that vertex is 180 minus x. Well, the sum of the angles in a triangle is 180 degrees. So looking at triangle ABC1, we can say, oh, this angle right here is x minus 40 degrees. So now angle A, B, C2, oops. Sorry, let's do angle ABC1 is x minus 40 degrees, and then angle ABC2 is the sum of those two above, which is 140 degrees minus x. And these two right here are the two possible angles at B. And their sum is simply 100 degrees because the x's cancel each other out. Any questions or thoughts about this one? Okay. Now let's take a look at number 12. I may have given a problem here that was a little bit too hard for the exam. This is a very challenging problem. This is a problem that I very often give to students who are, and I should have included a diagram. I apologize. I copied something over and I copied it into the wrong file. Though most of you wound up with the right diagram anyway, which is great. But a couple of you complained that this needed a diagram in order to make complete sense, and you're right. Though there's enough information here that, that a lot of you were able to guess how it was supposed to be drawn. And I apologize for that. Like I said, don't take your score here too seriously, but I'll go ahead and draw the diagram and we'll work this one out. I use this as a training problem for lots of Olympiad students, working to get up to, writing proofs, moving toward solving the first problem at the IMO, that level. It requires some clever insight, and almost nobody gets this without taking some serious time the first time around. So let's see. Okay, we'll put R up at the top. Actually, I'm just gonna get my own drawing right here. And we draw two angle bisectors. And these angle bisectors are PA and QB. And then we draw the altitude from R, or we draw the perpendicular from R to BQ. And we draw the perpendicular from R to PA. And we call these, let's see, R to PA is X. Okay, X and Y. And we want to show that XY is actually parallel to PQ, that bottom side in our triangle. And I haven't drawn this perfectly, so you kind of have to imagine that. And I gave 1 point to anybody who, tried to make like that angle equal to the angle at Q or something like that. Sometimes we like to think backward as to what would be sufficient to establish the premise. Okay, what can we do with the given information? Let's think in terms of congruent triangles or similar triangles, but in this case, Congruent triangles give us a little bit of a direction. We have some equal angles in this diagram, but it's not enough directly. We're going to have to draw some auxiliary lines. In particular, if we focus on X or Y, either one of them, I'll focus on X for the moment. We have a 90-degree angle at X. So if we extend our X, we create a second 90-degree angle. And these angles are within triangles where we can, they mingle with the angles at R. And I'll go ahead and label this point right here C. So what we see are triangles RPX and CPX. While they have two angles that are the same, what else do they have?
Share a side.
They share a side. Huh. Okay then, they share a side. So we have some more equal angle information. I don't know how we can use that. However, we can go ahead and extend our Y in the same way. And for the same reasons, we have triangle R, see, I'll call this D, R, Q, Y is congruent to D, Q, Y. Okay. So let's take a deep breath. Let's stop for a moment and ask, how can we relate that to the proposition?
Because of we're trying to prove that Q is parallel to PY, and we know alternate angle theorem, and we see that. No, I'm going on from the.
Let's think backward for a moment. So far, we've only been working forward, and I'll go ahead and tell you this: geometry is not my specialty, and so I have to be very deliberate about geometry because I don't see it as well as I see other areas of math. I think forward and I think backward a lot. Let's think backward. That'll be helpful. We want to prove two things are parallel. Well, how have we proven things are parallel in the past? Well, some equal angles. Angles give us parallel lines. And what gives us equal angles? Well, similar or congruent triangles. And if we're focusing in right here, we may notice something. Now, when we identified the congruent triangles that we identified, we said, hey, their side lengths are the same. It's always good to mark all that new information that we get, or at least a lot of it. Does anybody see anything interesting now? focus in on the part of the diagram where we have all that new information.
Triangle RYX is similar to triangle RDC.
Nicely done. Good. Yeah, sometimes, and this is something, once you see it, you can make the connection, but I'm going to put this into words. What we have is qualitative information. However, something like equal sides can be turned into quantitative information. Right? We have a 1-to-2 ratio of RY to RD, which is the same as RX to RC. And of course, we have a shared angle at R. So we have SAS, similarity. Triangle RYX is similar to triangle RDC. Therefore, they have equal angles. For instance, here and here. And that is enough to declare that that line and that line are parallel, those corresponding angles. Any questions or thoughts about this one? I decided to make this the last problem of the test here because I know this is a very hard one that I give often, and usually there are only a few students who get it at most. Usually when I give it, I have one correct answer or no correct answers at all. But this is a good example of a problem where, once you begin to see on this level, see the things where you can draw through points to create opportunities for new information, and that information winds up cascading within the problem that you're working on. It's a good lesson right here. Any questions or thoughts about this one? So just to mention, I think out of 5 exams, we've had 4 different high scorers, and David, I believe, was the high scorer of this week's exam, so nicely done. Any questions on any of the problems before we call it a day?
I was just wondering how sometimes how you process information. With like the previous question, there was a lot of lines there that were dividing different things. I might not have even seen the triangles that were there. And so, like, for example, the triangles that we used that were similar, and when we extended the perpendicular line, I might not have even seen them because there's so much to focus on. So how would you sort of discern and find, okay, I should focus on this or that?
Right. So part of the way that we improve as problem solvers is by experience. And when you, sometimes you will be looking at a diagram and you will make the clever step before anybody's ever taught it to you. The fact that you're all here means that most of you have done that before, right? On the other hand, as you work problems and don't solve them or read somebody else's solution or read a solution in a book or on the internet, ask yourself, how could I have seen that? At the end, ask yourself in retrospect, what did the solver see? And that may lead you to ask the question that I did: how can we make use of the equal angles in the diagram? How do we make use of equal angles? Well, with congruent triangles and similar triangles, those are 2 of the most common. It didn't seem like there was a very immediate use of similarity, but one way or another, we needed more information. We needed information to mingle with those split angles at P and Q. And so drawing through, extending where we had those right angles, that gives equal angles. And we've used those equal angles in several proofs, right, this week. It's one of those things that may seem hard now, but when you have seen a handful of problems, it will become easier. It'll become familiar. So it may seem crazy right now, but experience makes it normal. And as you have a few normalized observations like that, then then it doesn't look like there's so much going on in the diagram, right? As you see more, you learn what to focus on more often. And that's, it's not always going to be the case that you're going to solve every possible geometric theorem. No mathematician does. But experience will help you hone in on information that's more common, that seems clever now. Keep working problems. Any other questions?
Thank you.
You're welcome.
Please, when would the results come out?
Sorry?
Please, when would the results come out? Like, you have not sent it to us.
I don't exactly know how the results are sent out, so I can't answer that, but I know that all the papers are graded.
Mr. Crawford.
And by the way, there was one student who didn't send their first 10 answers. They only had problems 11 and 12, and the page for 11 was copied twice. So somebody needs to send in their answers to the first 10. Sorry, go ahead, David.
You mentioned that I was the champ. I got the highest score for this week, but going through my questions, I just realized that I didn't write my name on my paper. So how exactly?
Oh, I just saw an email sent out. Each week I've been getting an email from Joel saying, hey, these are this week's high scores.
Oh,
So
okay.
I think I can answer it a little bit. I can look into sending out the emails. I think we could just do it from CrowdMark, but the way we know is when you all submit, it's linked to your email account. So I think Joel knows which email maps to which one of you.
Okay, because when I realized, I got a little fright because in Ghana, when you don't write your name on, let's see, he would still deduct some.
Yeah, you don't have to worry about that.
Okay, so thank you very much.
Any other questions or thoughts? Okay, I'll see you all Monday, and we'll continue learning more about similar triangles.
Thank you, Mr. Crawford. Thank you, Ms. Wendy. Enjoy your weekend.
Thank you.
Thanks, you too.